According to Einstein, there are two things that are infinite: the universe and human stupidity. And he wasn't sure about the universe. This tongue-in-cheek quote might feel like nothing more than a light-hearted poke at the silliness of humans, but it's that second part that highlights the important truth. Our universe is an enigma. It is the home of everything. Every swirling galaxy and awe-inspiring nebula, every exploding star and every black hole. And yet, there is so much we don't know about it. What is the universe's structure? Is it finite or infinite? How did it begin? Where will it all end? Not even the greatest minds of the last 100 years knew the complete answer. We've come a long way since Einstein, and powerful tools like the James Webb Space Telescope have allowed us to peer through space and time, all in an effort to find details that hint at the nature of the reality we inhabit. But what do we know? And what is still obscured, thanks to vast distances and puzzling, invisible forces? What is the universe? It's time we found out. I'm Alex McColgan, and you're watching Astrum. Join me today in this cosmos-spanning supercut as we explore literally everything that has ever existed or will exist, otherwise known as our universe, and the incredible techniques scientists have utilized to better understand it. We like to go big here. With a topic this large, we're going to need to divide the problem up. So let's begin with what we know about the nature of our universe as it stands right now. In effect, what does the universe look like? This may sound like it has an obvious answer. It's a collection of galaxies all floating around in a dark void. But even 100 years ago, this concept was not what scientists believed the universe looked like. They thought that the number of galaxies that existed was exactly one: ours. But the key to disproving this belief and furthering our understanding of the universe into the 21st century came with our ability to measure distances. So with that, let's explore how we learned to gauge the scale of space. You may have wondered, with the vast distances between objects in space, and with the lack of a tape measure that big, how can scientists be sure they know the distances between us and other celestial bodies? Well, there are a few methods available depending on how far away the object is, each with a varying degree of accuracy. The first method is the most accurate, and in fact gives us very precise measurements. This is the parallax method. For those of you that don't know what the parallax effect is, it is where nearby objects appear to move more compared to objects far away as you travel parallel to them. For instance, when you look out of a side window in a car, everything close by whizzes by, but objects in the background stay reasonably still. How does this equate to measuring the distance between stars? Well, Earth orbits the Sun, taking 6 months to reach from one side to the other. Scientists can look at a star and record its position compared to distant stars beyond it. In 6 months' time, scientists can again record where the star is. Because we know the diameter of Earth's orbit is roughly 300 million kilometers, using simple trigonometry, we can work out the distance to the star. Is the star close to us? Then the differences in its apparent location will be much bigger. Is it further away? The star's position will only change very slightly because the angle is much smaller. This method works up until about a distance of 400 light years, as beyond that the change in its apparent motion can't be measured anymore. Earth's orbit would have to be a lot bigger before you could use this method for farther distances. Which is unfortunate because most things in space are further than 400 light years away from us. But thankfully there are very clever scientists out there that have come up with another method to judge distances without having to use trigonometry. Although it should be mentioned that this method is slightly less accurate. It's just simply the best we've got. It seems that stars tend to follow a pattern which can be seen on this Hertzsprung-Russell chart. Main sequence stars, which make up the majority of stars in the universe, can all be found somewhere along this band. Their temperature corresponds to their color, and most importantly, their brightness. Using stars that have a confirmed distance thanks to the parallax method, we can see how much a star dims due to the distance between it and us, and extrapolate that far beyond 400 light years. So, say we see a very blue star that we want to know the distance to. Once we know the star's precise color, we can tell how bright it would be if it were right next to us. We can then measure the star to see how bright it is from our perspective. Combining this with our extrapolated data, we can predict how far away the star really is. Obviously though, there is some margin of error in our predictions. This band is quite thick after all, not a precise thin line. So these two methods work for stars in our own galaxy, where they are still close enough to be resolved individually. But what about other galaxies? How do we measure the distances to them? Well, we would have struggled were it not for the universe being kind to us by gifting us Cepheid variables. A Cepheid variable is a very special type of star that changes in brightness periodically depending on their absolute magnitude. And some of these stars are very bright indeed, so much so that the changes in brightness can be detected by us all the way in a different galaxy. Timing the pulses in a Cepheid variable, we can know exactly how bright the Cepheid variable should be and how dim it is to us, allowing us to use the extrapolated data again to work out the distance to it and to the galaxy it resides in. This actually became the key to learning that other galaxies existed beyond our own, a discovery that began with the astronomer Edwin Hubble. Remember, our understanding of the universe 100 years ago was not very advanced. In fact, prior to 1923, it was widely believed that all the stars we saw in the night sky belonged to just the one galaxy, ours. Although some astronomers began to spot these fuzzy patches, actually galaxies, in the sky and postulated them to be island universes external to our own, this was not the mainstream idea. Most scientists believed that what they were seeing were just strange nebulae within our galaxy. Proof that they were actual galaxies in their own right didn't come until the 1920s, when American astronomer Edwin Hubble began studying one such object for himself. While studying what we now call the Andromeda Galaxy in 1923, Hubble realized that one of the stars he was looking at was a Cepheid variable star. This was particularly exciting because Henrietta Swan Leavitt had already described the period luminosity relationship of Cepheid variables in 1912, so Hubble could apply her theory to his new discovery. By measuring how regularly the star brightened and dimmed, Hubble could calculate how bright the star should have been, or its absolute magnitude. By comparing that to how bright it actually was, he could mathematically calculate how far away it was. Sort of like knowing that a candle that's further away from you is dimmer than one that's close by. Suddenly, he had a ruler with which he could measure the universe, and what he found out surprised him. The star he was examining was so far away, it had to exist outside of our galaxy. This opened up our understanding, but it wasn't long before another surprise arrived. By noting the Doppler shift of the light of the galaxies he was observing, whereby their movement makes light sources traveling away from us to appear redder, and light sources going towards us to appear bluer, Hubble noticed that almost all the galaxies he could see were not moving around randomly, but were moving away from us. He was able to see an expanding universe, something he had not expected. It felt like an affront, a universe almost like a mobile, dynamic, organic, and expanding entity. It was an observation so disturbing that even Einstein refused to accept it. The German theoretical physicist had just shaken the structures of scientific foundation by proposing an unimaginable transformation to our old notions about space and time. And even then, he could not accept that the entire universe was something dynamic and changeable. In fact, he was so convinced that the universe was a static entity, Einstein set out to modify his original equations by adding an extra element to stabilize the mathematics of the universe. This addition was called the cosmological constant. For Einstein, the idea that the universe was expanding was so distasteful that he initially couldn't bring himself to accept it. And yet, time and Edwin Hubble proved his static model wrong, making a cosmological constant unnecessary. But this raises an interesting question. Why are we so certain the static universe model is wrong? There are many answers to this. Interestingly, the very fact that space is black is one of the ways we know the universe can't be a static place. It simply can't always exist and never change. Have you ever looked up into space and wondered why it was black? Well, strictly speaking, there's a very few different reasons for this, but I wanted to discuss something known as Olber's paradox. Some of you may answer the question of why space is black with, well, there's nothing in between the stars, so of course it would be black, there's no light source. In a finite universe, yes, that is true. Even in the Hubble Deep Field images, which are some of the grandest exposures of all time, we see that you can look at a seemingly innocuous section of empty space and still find various sources of light like stars and galaxies. But even here, there seems to be gaps between the galaxies. And as we know, galaxies aren't a solid light source. In them are vast distances between even the most densely packed star clusters. Very basically, imagine a sphere around a light source. Let's focus on a section of that sphere. The intensity of the light reaching that section is reduced depending on the radius from the source, because the further the light has to travel, the more it spreads out over a larger surface area, meaning its intensity to an observer becomes reduced. However, if we lived in an infinite, static universe, a universe with infinite stars, no expansion, and with no beginning or end, the entire sky wouldn't be black, but instead as bright as the surface of a star, or even infinitely bright. This concept is known as Olber's paradox. This is because it wouldn't matter where you looked in the sky, in an infinite universe there would be a light source in that point, with every single micro arc second in the sky covered by a star at one distance or another. But you may say, what about clouds and dust that would obscure the view of background stars? In an infinite universe, these will also be as bright as stars as they receive and reflect so much light. This is one of the grand evidences that the universe we live in is not everlasting, but has a beginning, and so probably also has an end. It is also evidence of the expansion of the universe. The Hubble constant has shown that the universe is expanding at roughly 70 kilometers per second every 1 megaparsec. Given that the universe likely has an age of roughly 13.8 billion years, and because we observe that it is dynamic and expanding, it means that there is a sphere around us on Earth that we can't see beyond, because galaxies that are beyond that sphere are moving away from us faster than the speed of light. This means that even with a telescope capable of infinite magnification, there would be patches of space in our sky that contain nothing at all from our perspective. Olber's paradox was evidence against an infinite, static, eternal universe. But there was also proof in favor of the alternative. Specifically, something we see happening within the redshift of stars seems to seal the deal. The galaxies towards the furthest reaches of what we can see have another noticeable characteristic. They are not just redshifted, but the further away they are from us, the redder they appear. They are accelerating, with distant galaxies becoming redder due to the stretching of light wavelengths through the expansion of the universe. The redshift of galaxies can become so extreme that light that was emitted in the visible light spectrum billions of light years away is stretched so much that it eventually reaches us in the form of infrared wavelengths, beyond our eyes' capabilities to see. It's always useful to examine ancient objects within the universe to see if our theories are correct. Sometimes those objects come to us. On the 1st of July 2025, astronomers in Chile spotted an interstellar comet 7 billion years old, half the age of the universe, older than the Sun, in our solar system. While not from the Big Bang era, it's a fascinating object to help us understand galaxy formation. News like this is best when it's not just reported on, but analysed. And for that, I turned to The Economist, the advertising sponsor of today's video. I stumbled on the interstellar comet story in The Economist, and I must say, I was impressed at the breadth and depth of the topics they cover. Not only do they bring you news from correspondents across the globe, but they go further than breaking news. They offer insight and analysis on the things that matter: science, business, and world events. Their app gives you access to videos, podcasts, and audio versions of their articles, so you can stay informed while you're on the go. Astrum viewers can get a special 35% off discount on an annual subscription to The Economist, so scan my QR code or follow the link economist.com/Astrum in the description below to check it out. Hubble's discovery was eventually recognized by the wider scientific community. Galaxies were moving away from us. But this was not the end of the discovery. It wasn't long before scientists realized that if galaxies were moving away from us now, they must have once been a whole lot closer, shedding light on not just the universe's shape, but also its origins. The theory of the Big Bang was born. The idea was simple. About 13.7 billion years ago, everything that is in the universe today was crammed together into a space the effective size of 0. At the very beginning, not even atoms existed. It was just a hot and dense soup of fundamental particles. Since the beginning, the universe has expanded rapidly. As it expanded and cooled, atoms formed and stars were born. One interesting consequence of this is that the universe's expansion, combined with the constant speed of light, has turned the universe into a time machine. If we look at any region of space, we don't see galaxies as they are, but as they were. Galaxies we see in the foreground are much more developed, forming the more elegant and defined shapes you see here. That is because we are seeing these galaxies as they were only millions of years ago. They've had billions of years to form since the start of the universe, and so they look much more mature and developed. On the other hand, as we look at more and more distant galaxies, these galaxies appear younger. Galaxies that are billions of light years away appear as they would have shortly after the Big Bang, because the light emitted by them has taken that long to get to us. They look misshapen, and there is a lot of star formation going on within them. But in reality, it's important to remember that these galaxies are just as old as ours, and they no longer occupy the location where we can see them. They are probably much further away now because of the expansion of the universe. It is also important to realize that there is no center of the universe, or conversely, that everywhere is the center of the universe, because it doesn't matter where you are, here or a billion light years away, everything is expanding away from you. Everything is expanding away from everything. Just as a side note though, gravity combats the effects of the universe expanding. That's why superclusters of galaxies exist. And the universe has a filamentary structure. The gravity from galaxies is attempting to keep clumps of them together, even though the expansion of the universe is also pulling them apart. What you end up with are filaments with empty bubbles or voids in between that will only get bigger as the universe expands further. We mentioned earlier the term the Hubble constant. This is how fast the universe is expanding, currently thought to be around 70,000 kilometers per hour per million light years. So, for a section of space 1 million light years across, it expands by 70,000 kilometers every hour. A section 100 million light years across would expand by 7 million kilometers every hour. The current values of Hubble's constant implies that the entire universe is expanding faster than the speed of light, explaining why there is a sphere around us that we will not be able to see beyond. Everything within this sphere is the observable universe, another term you've probably heard of before. We can't see or detect anything beyond the observable universe, which is why we have to deduce whether the universe is infinite or finite, rather than just seeing for ourselves. Of course, if it is finite, it couldn't have an edge, and would have to loop around because, well, the universe is just that, everything that exists. What would be beyond the edge of the universe otherwise? It can appear that we are the center of the universe, the epicenter of the Big Bang, but this is an illusion. So where in the night sky do astronomers look to see where the universe started? Well, the answer is everywhere. Because the universe has always been the whole universe, it has just changed in size from being very small to very big, but it doesn't have specific coordinates because it is an explosion of the coordinate system itself. So how long ago did this happen? And how do we know? Well, aging our universe is not as simple as you might think. While modern day science believes the universe to be 13.8 billion years old, I do have an example of a star that throws a spanner in the works. A newly discovered star called the Methuselah star, which apparently is older than the age of the universe. But let's get back to that first part. 13.8 billion years old. How did we come to that figure? As already mentioned, we currently see that the universe is expanding and cooling. Everything is moving away from everything, excluding forces like gravity keeping things together. We already know the speed of this expansion, the Hubble constant, which is 70,000 kilometers per hour per million light years. So the obvious conclusion is that if we wind this all back, we'll be able to calculate exactly when the universe started. We do need to assume a few things about the universe first though. 1. The universe is uniformly dense on the largest scales. This seems wrong. It's clearly not uniform. There are superclusters full of densely packed galaxies and supervoids containing not much at all. However, like stars in a galaxy, zoom out far enough and suddenly everywhere looks the same. So we assume the universe is homogeneous. As a result of that, not only is matter distributed evenly, but 2. We also assume the universe's laws and properties are the same throughout in any direction. And 3. We assume the Big Bang occurred in all locations, everywhere at once, which, as we already mentioned, seems to be the case. Under the laws of general relativity, if these 3 things are true, then there is a connection between how old the universe is and how it expanded throughout its history. So this is what scientists did. Using 3 different instruments, all looking at different aspects of the universe, all the answers have come back roughly the same, 13.8 billion years, with an estimated 99% accuracy. But there's another method, which has thrown a bit of a spanner in the works, and that is to measure the age of stars. Certain types of stars are very short-lived, going supernova in a matter of a few million years. Others could last for trillions of years. Not that we've seen one that old for obvious reasons. In fact, following the evolution of stars, we haven't really seen any older than about 13.2 billion years old. But this does mean that long-lived stars that formed as matter was coalescing shortly after the Big Bang would certainly still be around today. And this is where our friend Methuselah comes in. Methuselah is a metal-poor star, meaning it is very old and incredibly rare, and most special of all, it is only about 200 light years away from us, which means we can examine it relatively closely. Based on its evolution, it is an estimated 14.5 billion years old, give or take about 800 million years. This means it might have disproved the 13.8 billion figure. So, do we really know how old the universe is? Roughly. It wouldn't be surprising to see this figure change as our technology improves. We have the Nancy Grace Roman Space Telescope coming out soon, and the James Webb Space Telescope is bringing in data already, and what it's seeing is certainly upsetting a lot of our cosmological models, with galaxies evolving too quickly to match our predictions. This may simply mean that galaxies evolve faster than we anticipated, but it might also eventually shift our estimate for the universe's origins. Exciting times. Although I don't think we'll see this figure vary more than about 1 billion years in either direction. A lot of the data is grounded in some very solid science, even if we don't have all the answers. The Big Bang model, or some variation of it, does the best job so far at explaining why our universe looks the way it does. But it doesn't solve all the mysteries about our universe's structure. In fact, it created a few. There was one strange fact about the way galaxies were moving that troubled scientists. One that the Big Bang did not quite account for. It wasn't just that galaxies were moving away from us, they were accelerating away from us. Yes, we mentioned that already. But acceleration requires energy. Where was this energy coming from? Nobody seemed to know, but it seemed to permeate everywhere.
To fill this gap in their knowledge, scientists came up with the idea of dark energy. Applying general relativity to this expanding model universe and comparing it to the latest observational data, scientists realized that the particles we could see, known as baryonic matter, made up only 5% of the universe. Somewhere out there is a shortfall of 95%. It was the only thing that made sense. Matter was congregating strangely, as if something invisible with gravity was pulling it closer together. Scientists called this substance dark matter and attributed to it 27% of that mysterious 95% shortfall. But matter was also being pushed apart. The remaining 68% of the universe had to be the energy that was responsible for that. Undetectable, invisible, but everywhere. The maths proved it. There are a few different ideas about the nature of this energy. For starters, Einstein's cosmological constant raised its head again, this time with a new application. Einstein originally came up with the idea of such a constant as a way of perfectly counteracting gravity, a push to balance its pull, to ensure the universe neither expanded and contracted. But if you start with a bigger cosmological constant, you'd get a universe that tipped into constantly accelerating away from itself, just like we see in real life. Einstein hypothesized that empty space might not truly be nothing, but that it held energy, and it could and did create more of itself. This creation of space would create more energy, increasing the pushing power as time went on. It's unclear why space would have this property though. It was more a recognition that it seemed to than an explanation. To fill the gap, quantum mechanics stepped up to the plate. Scientists of this school hypothesized that perhaps virtual particles were to blame for this extra energy. Virtual particles are pairs of atoms that simply pop into existence as a quirk of the quantum wave function that exists everywhere. They don't stick around for long, as they meet and cancel each other out again, but in the moment before their annihilation, they could, conceivably, push against things, exerting force. This theory had some experimental evidence to back it up. There is some suggestion that virtual particles do in fact exist, at least in some form, but when scientists tried to work out how much energy such particles could create, if this was happening in the vacuum of space, their answer proved to be too large. And not just by a little, by about 120 zeros. When your answer is too big by 120 zeros, there's likely something wrong with your maths. Indeed, this answer got the dubious accolade as the worst theoretical prediction in the history of physics. The third main idea is that of a varying cosmological constant, So not really a constant at all, but rather an adjusting field, like an electrical field or a gravitational field, that accounted for this repelling force throughout space. This force was called quintessence. And it might be the fifth fundamental force of existence, if it really does exist. The problem with this idea, however, is the same as the issue with the cosmological constant. There is no explanation as to why it exists. In short, this is still a very poorly understood field of study. More information would be needed before accurate conclusions can be drawn. Spotting something invisible is naturally hard, but studying dark energy through its impact on the universe around us is already underway. Different observatories are attempting this in different ways. BINGO, the Baryon Acoustic Oscillations from the Integrated Neural Gas Observations Telescope in Sao Paulo, Brazil, is a land-based radio telescope that intends to monitor the radiation given off by hydrogen atoms in the dark patches of space between galaxies, to see if there are any unusual distributions of matter that might point to the influence of dark energy. A curious fact about the universe is that matter clusters in waves. It is statistically more likely that there is a distance of around 500 million light-years between any two galaxies than any other number. It's thought that this is to do with ripples in the early universe right after the Big Bang that have coalesced into more solid forms of matter as the universe cooled, locking those ripples into place. Seeing the gaps between such ripples, even in the darkest corners of space, could be very instructive. However, if you really want to spot dark energy's hand over time in space, you need to go big.
And it's for that purpose that, in 2023, ESA launched the Euclid Space Telescope.
Euclid is a wide-angle telescope with a 600 megapixel camera designed to capture visible light and infrared radiation from over a third of the sky. Euclid's mission is to survey this massive patch of sky with a level of detail and sharpness that's 4 times greater than previously achieved by ground-based telescopes. It wants to map everything, going back 10 billion years. The hope is that in so doing, it'll be possible to create a 3D map of the influence of dark energy, with the capacity to see how dark energy's influence has changed or remained constant over all that time.
Euclid is looking at individual stars too, but its main objective is sheer volume. This way, the pattern of dark energy will hopefully emerge. Euclid has already started capturing images and has just recently released its first batch of survey data. Euclid has, so far, spotted 26 million galaxies in a patch of sky 300 times the size of the full moon, and scientists are already diving into the treasure trove of data, using AI tools to help classify and categorize what they're seeing. And remember, by the time it's done, this dataset will include 1/3 of the night sky. Who knows what discoveries will come to light?
So, fingers crossed that this mission can shed some light on the mystery that is dark energy. For now though, this enigmatic force remains a mystery. It's only because of the universe's expansion that we are aware of it at all. It is otherwise undetectable. But as it makes up over 60% of all that exists in the universe, it must be around us all right now. It pushes on us, just as it pushes on every other galaxy, and slowly but surely, it forces all things apart.
Understanding this force is vital if we want to truly understand our universe. The nature of dark energy helps us know how the universe began, and also crucially, how it will end. So as we head into the final chapter of this video, let us turn our gaze to the future of the universe. A future where there are no longer any planets or stars or galaxies. No longer any atoms or molecules or life. A future where the universe is lying on its deathbed. How long do we have until that future is here? And is there an afterlife for the universe? Depending on the nature of dark energy, the accelerated expansion of our universe can grow stronger, settle down, or even reverse course. And rather than just examining one of these fates, we've decided to collect them all into one big flowchart to serve as your one-stop guide to the end of the universe. At the top of the flowchart is what dark energy is, and at the bottom is how we all die. Most cosmologists would agree that dark energy is likely to fall into one of two main categories. First, the most popular theory is that dark energy is the energy of the vacuum itself. Second, the leading alternative is that dark energy is the energy of new fields in the universe that we simply haven't discovered yet. Since fields are just a way to represent collections of particles, this would mean that dark energy is made from a new form of matter, new types of particles, beyond electrons or quarks or anything else we know of today. From these two categories, our flowchart is going to branch out into theories of dark energy that are wildly different from each other and predict all sorts of catastrophic futures. On the vacuum energy side, we need to consider whether the vacuum itself is stable or whether it can jump into a state of even lower energy through a process known as quantum tunneling. A stable vacuum is by far the simplest scenario. It means the dark energy will continue to exist for an eternity in the same form it takes on today. Our universe will accelerate forever, growing infinitely larger and colder in what's called the Big Freeze. The good news is, you wouldn't notice anything changing here on Earth, or even throughout the Milky Way, since there's enough mass concentrated in this small region to counteract the gravitational repulsion coming from dark energy. But if you zoom out beyond that, you'll notice that distant galaxies are being accelerated away from our own in all directions, eventually crossing a threshold known as the event horizon. Just like with a black hole, once you cross this point, you can no longer communicate or interact with the world you've left behind. That means that, one by one, we'll lose contact with all galaxies beyond the local few where gravity is strong enough to keep us close. All that will remain of them is a dimming, reddening light from the moments before they cross the event horizon. Eventually, this light will become so faint that it too will be unobservable, and future generations of astronomers, billions of years down the road, might have no idea that anything ever existed in the universe beyond the Milky Way. If you're wondering what will become of the stuff inside the Milky Way, it dies a relatively boring death. The second law of thermodynamics says that systems will always tend towards a state of higher entropy. When stars fuse hydrogen into helium and emit light as a byproduct, when planets heat up and winds soar across the atmosphere, and even when you eat a carrot and wait for it to come out the other side, all of those processes increase entropy. But the entropy of the Milky Way can only grow so large. Eventually, stars will run out of hydrogen to fuse, planets will be left to freeze, winds will abate, and there will be no more carrots left to digest. Matter will have nothing to do but collapse into black holes, and black holes will evaporate into a pool of radiation. What we once called the Milky Way will be in a state of total thermal equilibrium. Nothing will be happening. There will be nothing to happen. This fate that awaits the Milky Way is sometimes called heat death. Not because it's hot, in fact it will be quite cold, but because there will be no more heat flow, no more temperature gradients, no more transfers of energy from one place to another. Admittedly, it might take a while to reach heat death. Some estimates place it at 10 to the power 106 years away, or 10 to the power 96 times the current age of the universe. But if dark energy really comes from a perfectly stable vacuum, then there will be no avoiding it. Heat death is coming. There is one possible silver lining at the end of this story, however. It has been conjectured by Sir Roger Penrose, a Nobel laureate and brilliant physicist, that heat death might not be the end of our story, but merely a new beginning. In his model known as the conformal cyclic cosmology, Penrose proposes that the radiation-filled universe in the infinite future will be indistinguishable from the state of the universe at the Big Bang, and indeed may be one and the same. Each eon of infinite expansion in this model merely leads to a new Big Bang and a new cycle of cosmology. There isn't much evidence in support of this hypothesis as of yet, but it may be a source of hope to cling on to if our universe ends up heading towards a big freeze. You and I would not survive, but maybe the universe could, and at least that's something. If the idea of a big freeze scares you, I got some good news and some bad news. The good news is that there are reasons to believe that even if dark energy comes from the vacuum, that vacuum state might not last forever, meaning we might not be headed towards a big freeze at all. One reason to doubt the stability of the vacuum comes from observation of the Higgs field. Current measurements from CERN indicate that the Higgs might have a lower energy vacuum state than the one we live in, though it could take something like 10 to the power 100 years to tunnel into this preferred vacuum. To paint a mental picture of how this all works, we can imagine an apple falling off a tree, hitting our friend Isaac on the head and rolling off into a small dip in the grass. A short distance away, there's an even bigger dip, which the apple would absolutely be drawn towards if not for the barrier blocking its path. Classically, the apple is stuck, but quantum mechanically, the apple can and will tunnel through the barrier into this low energy state if you just wait long enough. The Higgs field works the same way, with its different vacuum states corresponding to the different dips in the grass. A second reason to doubt the stability of the vacuum actually comes from string theory. While string theory hasn't made any quantitative predictions, it's given us some pretty strong hints that stable vacuum states with positive energies are really hard to come by. String theory also predicts the existence of new fields that could conceivably tunnel to different vacuum states much faster than the Higgs, say within the next trillion or even 100 billion years. Here comes the bad news though. If we live in a metastable vacuum that can decay at the whim of quantum mechanical fluctuation, we've got bigger things to worry about than the big freeze. Quantum tunneling into a more stable vacuum won't just affect the expansion of space, it can also fundamentally alter the properties of particles and the laws of physics governing our universe. If the Higgs field falls into a new vacuum state, ordinary particles like protons and electrons will have completely different masses, and atoms and molecules as we know them will cease to exist. Or, if we tunnel into a new vacuum in the string theory landscape, our universe might suddenly contain new particles we've never seen before. In either case, life on Earth would all but certainly be toast. As for the universe as a whole, in this scenario we can't predict its fate more precisely without more information about the new vacuum we fall into. Let's step back and take a look at the other side of the flowchart, where dark energy comes from the presence of new fields rather than the vacuum. There are different ways in which fields can evolve over time, which would dictate the future trajectory of our universe. Unlike vacuum states, which would have perfectly constant energies between tunneling transitions, fields can continuously gain or lose energy over time. Just like a ball rolling across a rough patch of grass, fields experience friction as they evolve, so it's most natural to expect their energy to decrease. But physicists have shown it's possible to have exotic types of fields called phantom dark energy that overcome this friction and actually gain energy over time. These exotic fields wreak absolute havoc on the universe. Because their energy is growing everywhere and all the time, they eventually overpower the energy from all other forms of matter, even within the Milky Way. This increase in energy heats up the entire universe, fully reversing course from all the cooling the universe has done over the past 14 billion years. In this scenario, the expansion of space doesn't just continue to accelerate, but it accelerates so fast that any region of space will grow to infinite volume in a finite time, maybe even just a few billion years from today. And if you want to call for help, that gets increasingly harder, as the cosmic event horizon we spoke about earlier will shrink down to the size of our galaxy, then our planet, then our home, and then us. As this is happening, the repulsive gravitational effects of phantom dark energy grow ever stronger, ultimately tearing apart all of the molecules, atoms, and nuclei in the universe into their constituent parts. Then we hit the singularity. This new kind of singularity, where the universe is infinitely big and hot rather than infinitesimally small and hot, has been called the Big Rip. But I'm still hopeful that this grim ending from phantom dark energy exists only in the minds of theorists, while the real dark energy in our universe behaves more peacefully and loses energy over time. So what would fate have in store for us then? Here's where our flowchart starts to get a little messy, because there are so many different ways a field can evolve over time. There are two main questions that have to be answered to predict the fate of the universe in this scenario. First, can the dark energy field have negative potential energy? And second, does the field's energy change slowly or quickly? If the field's energy is always positive and it loses energy very slowly, it would hardly be distinguishable from vacuum energy. In this case, it would be headed towards another big freeze. On the other hand, if the field's energy is drained away very quickly, the universe would soon have no dark energy left at all. It would stop accelerating, and its future would depend entirely on its spatial curvature, or the shape of the universe itself. A flat or open universe would eventually evolve towards heat death, but there would be no cosmic event horizon to prevent us from communicating with galaxies as far as the eye can see. This may be the most peaceful of all the possible futures for the universe. On the other hand, a closed universe would eventually stop expanding, reverse course, and collapse back in on itself, which sounds less peaceful. This kind of recollapse is known as a big crunch. Having a closed universe is just one of two paths that can lead to a big crunch. The other way to see our Milky Way crushed to smithereens is for the dark energy field to reach a negative potential energy. At that point, it will only be a matter of time before the universe stops expanding and begins to contract. During this contraction phase, gravity turns cosmic friction into what theoretical physicists call cosmic anti-friction, speeding up the field's evolution and giving it more energy rather than draining it. If the field gains energy slowly, there will be plenty of time for the universe to recollapse and experience a full-on big crunch. On the other hand, if the field gains energy fast enough, the universe could reach a temperature mimicking conditions at the Big Bang at a rate so fast that this would all occur before the Milky Way is even predicted to collide with Andromeda. Even though space does contract in this scenario, it doesn't crunch. In fact, the amount of contraction is hardly noticeable by the time Earth turns to toast. So, what happens next? Models suggest that if the universe reaches extremely high temperatures while contracting, it could be forced to transition into a new phase of expansion, where it has time to cool off once more. This transition is called the Big Bounce. In fact, the universe could go through a big bounce following a big crunch too. These scenarios open the door to a new type of cyclic universe, entirely different from Penrose's idea, which we've discussed in a previous video, in which the universe goes through an infinite sequence of expansion, cooling, contraction, and reheating over and over again. In this picture, even our Big Bang 14 billion years ago could have actually been a big bounce, connecting our own cycle of the universe to all those that came before it. This wraps up our master flowchart for all the different ways the universe could end. It could freeze to death, be ripped to shreds, be crushed to oblivion, or simply heat up so quickly that it bounces into a brand new life cycle. We might not have any certainty yet, but even just narrowing it down to 4 possible options is already an enormous feat of science. So there's a great new topic for small talk with strangers and dinner conversations. You're welcome. So, there you have it. Our universe, present, past, and future. We may not know all the answers, but that doesn't stop the answers we do have from being jaw-dropping. Our universe may not last forever, and it certainly is constantly changing, but that doesn't stop it from being incredible. And as we continue to explore its vast reaches, either through telescope or maybe even one day physically traveling there, who knows what mysteries we will continue to uncover. The nature of reality is perhaps the biggest question of all. So as you sit there, remember, you are a piece in a vast cosmic puzzle. You are a part of the same system as black holes and supernovae, and you share in their brilliance. You might be small, but you too are a marvel, because at the end of the day, we're all part of the same incredible universe. Thanks for watching. I was honestly blown away by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 patron member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.